Hello, this is Mrs. Vrobel. I hope that you are well. I am praying for you and your family, and I encourage you to stay safe and also to be kind to those around you, especially in these trying times. What I'm going to have you do is I'm going to split this into two parts. I want you to take notes along with me for each part of the video, and then I have a activity that I want you to do at home with a couple friends or family members. So in this section, we're going to start talking about equilibrium, and I'm assuming that you have some knowledge about equilibrium. You probably feel like you're out of equilibrium right now because your normal life is no longer normal, and I would completely agree with you. The interesting thing in chemistry is that you could have a bond or you could have an intermolecular attraction, and we could potentially break those attractions or those bonds. So we're talking about like covalent ionic, or for intermolecular, we're talking about dipole-dipole, hydrogen bonding, or London dispersion forces. In addition to breaking bonds, we can also form bonds. So what does this mean? Well, what this means is that actually this is a dynamic process, and from now on, you need to not assume that a reaction is always going to go from left to right. It could go in reverse. So the reaction that you see listed there, this is actually the Haber process. It was created by, I think, German or Austrian. And he essentially took nitrogen gas with hydrogen and he created ammonia. And this was the first time they were able to develop a fertilizer which enhanced agriculture, because at the time the world was starving because they didn't have enough fertilizer. They didn't know how to increase agriculture, and this is what helped. So when you are looking at reactions, please remember that they are either forward or negative. Now, what kind of reactions could do this, or what kind of processes can do this? We are talking about either condensation or evaporation of water. It could be dissolution or dissolving of a salt. We'll eventually talk about acid-base reactions where they are reversible. Now, the characteristics of a system at equilibrium, don't assume that concentrations are equal. So I'm saying that the reactants concentration, and we'll talk more about what kind of concentration, they are not going to be the same as the concentration of the product. So you could have a difference in concentration of reactants and products. Now, with equilibrium, the forward rate, so going from left to right, is equal to the reverse rate. So that's going from right to left. And the other thing that we want to be aware of is the fact that both reactants and products are present. You're going to see that some reactions you start off with just a reactant and then eventually you create a product. But there's always going to be some reactant and some product in the expressions, and we'll talk about that next here. Okay, so equilibrium constant. We need to take into account the conservation of mass. So that means that we need to keep track of all the different concentrations, and you'll see that we get really good at doing that. Now there are two types of expressions. There's Kc and Kp. So when you're talking about Kc, you're talking about molarity. And when you're talking about Kp, you're talking about atmospheres. So I'm going to show you how to write an expression and keep conservation the same. So like I said, you have Kc, and when you write an expression, notice it has to be from a balanced chemical equation. You can't do it without it. And it's always products over reactants. And when we're looking at the products, we're looking at the coefficient of each. So when I write this, I'm going to write in brackets ammonia. And notice that it has a coefficient of 2, so I have to make that its exponent. And then I have nitrogen, which is 1 reactant to the first power. And I have hydrogen gas, which is to the 3rd power. So please be aware, whenever you have coefficients, they become the exponent for the equilibrium expression. Now Kp is slightly different. So to let the reader know that they're dealing with gases, we express it differently. And I'm going to use parentheses instead of brackets because I'm talking about atmospheres instead of molarity. So I'm going to rewrite the whole thing. The only difference is instead of brackets, I'm going to use parentheses. Okay, so notice that we're talking about molarity when we talk about Kc, and we're talking about atmospheres when we're talking about Kp. So I will give you some examples of actually plugging in the numbers in a little bit here. Okay, don't worry about example, I'm just going to skip that part. So when we talk about the equilibrium constant, please remember K is products over reactants, and they're to some power. So you got to pay attention to that, and that's based on the balanced chemical equation. Now notice that for this first equilibrium constant here, K is greater than 1. So what does that mean? That means that the concentration of products are greater than the concentration of reactants. So the numerator is bigger than the denominator. So that's when K is greater than 1. Try to fit this so it's okay, now you could have the opposite, which is K is less than 1. So when K is less than 1, you're going to have the concentration of reactants being bigger. Than the concentration of the products. So the denominator is bigger. Okay. Now, obviously, if you have a situation where K is very tiny, we're going to talk, I'm sorry, when K is very, hold on a second here, guys. Yeah, you know what, guys? For now, just ignore that. I don't want to talk about that right now. The important thing is that when we are talking about K, so the equilibrium constant is temperature dependent. And you'll see why in a little bit. Okay, here we go. So I just want to talk about this set of graphs here, and then after that I'm going to give you some time to take a break. Okay, so I have two graphs here, and here I'm gonna get rid of this. Ugh, sorry guys. That was from a previous video. Okay, so what's happening here is products at the beginning of a reaction are 0. And that's to be expected because we're not preloading a beaker full of material with a product. We're starting off with just reactants. Now, you could have the opposite. Sorry, my pen got crazy here. You could have the opposite with reactants where you're starting with a ton of reactants. So notice that you're starting off with 40 reactant molecules and you have 0 product molecules. Okay. Now this is where people get a little confused. They think that at this line that equilibrium is taking place, and that is not true. Okay. When they're crossing, that just means their concentration is the same. Okay. Please remember that equilibrium is when the forward rate equals the reverse rate. So that is equilibrium. It is not concentration. So concentration may not be equal. So actually, what does this mean? Where you see it flatlining, so there's no change in concentration, that is equilibrium. Because that means that the amount of product that is being made, its rate is the same as the amount of reactant that's being made. Now, if you look, the concentration of product is greater than the concentration of reactant. So that means that the numerator is bigger than the denominator. So as a result of that, K has to be greater than 1. So for this top graph, K is greater than 1. Now with the bottom graph, something different is going on here. So once again, the products at the beginning are 0, and the reactant at the beginning is 40. So as a result of it, we're starting off with no products. We have all reactants, but something different is coming into play. So instead of having them share a concentration at some point, they never do. And as a result, when you're looking at concentration, let me just use a different color here. I would argue that concentration flatlines right around here. So as a result of it, equilibrium probably happens a little bit sooner than the previous graph. So you could argue that the concentration of the reactant is greater than the concentration of the product. So what does that mean? That means that the denominator is bigger than the numerator. So as a result of it, the equilibrium constant is less than 1.